Hello, in this video I want to present different concepts related to a question that was asked in a what if column by Randall Munroe. Can you burn paper with moonlight? And the related question would be, can you concentrate the light from the sun to such an extent that you can achieve a temperature as high as you want, much higher than temperature at the surface of the sun? And in both cases the question is no, but while this seems like kind of an obvious question that it should have a simple answer, there are a lot of interesting physics in that, which I want to present in this video and in many follow-up videos, because there won't be enough time in this video to present everything that's interesting from this problem. So this video will present general qualitative and semi-quantitative concepts related to this problem, and the next video will talk about the math of what will be discussed in this video. So this video would present mainly the concept of étendue. So étendue is a French word that means either spread or width or extent. And it's a measure of, let's say, how big some beam of light is. And the beam of light could be big in two ways. It could be big because it's a large area. Let's say you have a small laser that's small output, it's a very small beam, and you have a larger laser with the wider beam, and the same angular spread, like the same type of light. Or a beam could be large because it's either emitted over a narrow beam or a wide beam, and the wide beam will of course be spread over a larger distance. And we define broadly the étendue as, could be seen as the product of the area times the solid angle sustained by the beam. Now, the solid angle, for those who don't know what a solid angle is, it's basically the generalization of an angle, but to 3 dimensions. An angle is in 2 dimensions, and it basically tells us about the spread of something that goes along a triangle. For example, here you have two lines, and you can see that they can span a triangle. They stop here, and the angle here is how far apart these two are. Well, the solid angle can be seen as, if you for example, you have a cone, can be seen on how big this cone is. How big is this angle that spans the cone? And we can show that étendue can never decrease. And in ideal systems in which we have reflection and refractions, and in which there are no losses, there's no diffusion or anything, étendue is conserved. So more formally, we define the étendue of an infinitesimally small beam of light that have a very small extent and comes over a very small surface as n squared, and the n is the index of refraction of the medium in which we are, times ds times cos theta, I will show what theta is, times d omega. And theta is simply the angle that the small beam makes. So we have this setup. This is a beam that extends over a very small solid angle d omega at an angle theta with respect to the normal to an infinitesimally small surface of area ds. And why is this conserved? Well, intuitively, we know, for example, that when light is reflected, let's say we have this beam here that comes here and is reflected. Well, this here will not change, because when light is reflected, this light will be reflected with the angle of incidence. This ray of light will be reflected with its own angle of incidence, and every light will not be deviated except for reflection above the normal axis. One way to see it is that when you look at objects in the mirror, they don't change size. Basically, they keep the same size. And the area of the beam wheel doesn't change, it's a point reflection. So for reflection that works. And for refraction, well, for refraction, we know that, for example, if you look at an object in a telescope, it takes the light over a large area. That's why you see the stars becoming brighter. So you look at something that's not visible to the naked eye, or very difficult to see, for example, the planet Neptune. And you look at Neptune in a telescope, and two things will happen if you've got a big enough telescope. The first one is that you will see now the planets, so the light is concentrated over a small area. It takes the light over a large area of the telescope, concentrates it to a small area, and you will be able to discern the size of Neptune. It will become a small disk. So what happens is that the light that was over a very small angular distribution, when it came to you, now is wider, because if something looks wider, it's because light from each extremity comes from wider angles. So basically the light has been spread out in angle. So that's basically how you can understand why a tangent is conserved intuitively without doing the math, which I will do in the next video. Now let's see what happens to answer the question to our initial problem. Can you burn paper with moonlight, or how much can you concentrate sunlight? Okay, so let's suppose you have a source here. I put in the sun, for example. That's in a medium of index of refraction n, and of course for the sun the source is in vacuum, so n is equal to 1. And we have a system here that will manipulate our light waves with reflection or refraction. And we know that by conservation of étendue, if the light comes in over a certain angle, over a certain surface A in, and goes over a different surface of area A out, and over an angle theta out, there will be conservation of étendue. And when we do the integral of the small element of étendue that we had in our last board, we get the result that the product of the input area times the square of the index of refraction times the square of the sine of the input angle is the same as the same quantity for the output angle. And that gives us a limit on how much concentration we can have. Intuitively, you can understand that as we get to a smaller surface, the output angle will increase, and at some point the output angle will reach 90 degrees. So basically, you have your output here, and whoops, the light rays are going in just in this direction, like they're going parallel to the output surface. And if you wanted to get the area even smaller, well, the light rays will come back on themselves, so that wouldn't work. Like this, the light rays are going backwards, and you're not concentrating light anymore. There's no way to get light that going this way to get over a focus point here. Doesn't work. So what happens is that when the output angle reaches 90 degrees, this quantity becomes 1. And let's suppose for the moment that the input and output index of refraction are the same. For example, here it's vacuum and air, but they are so similar to each other as that doesn't matter for our practical purposes here. And we have the concentration, the maximal concentration, which is equal to the area at the input over the area at the output, is equal to 1 over the square of the input area. It's just basically rearranging these terms. We switch this term on this side of the equation and this term on this side of the equation, and we get this expression. So it turns out that for the sun or the moon, which are basically the same size, that's why we have eclipses, the alpha angle is about 0.7 degrees, and the maximal concentration is about 45,000 times. So on the next board, I will have some numerical examples as to what we get as far as light concentration is concerned. And also, I will discuss some objections that you can see if you look discussions of this problem on the Physics Stack Exchange forum. This is also one of the places where the interesting physics happens, because for now you have basically to take my word for it, because there are some calculations that I haven't made that I will make in the next video. You can go on the Wikipedia webpage to look at them. But if you look at all the discussions of this in various forums, they are basically two misconceptions that people have that I will address. Okay, so now let's see what happens with the sun. We've seen that the maximal concentration, if you put in the numbers in the equation I had in the last board, is about equal to 45,000. And of course here I'm just working with approximation. I don't want to recopy exact numbers. You can use a calculator and do the exact calculation, and you will see that everything fits perfectly. Now we know that the power coming in the upper atmosphere from the sun is about 1361 watt per square meter. And if we concentrate this 45,000 times, we'll see that payout, the output power, equals about 1361 times 45,000 watt per square meters. And you would get at something that's about 61 watt per square millimeters. And that's actually the power of sunlight at the surface of the sun. Well, I think that the actual number is 63, but here I've made various approximations, and that's where we lose details, and this figure may not be 63 exactly, but if you do put in the right numbers, you will get the exact result. And first we see that it's a very large number, 633 watts. So imagine all the power in one of those old 60 watts incandescent light bulbs. Instead of being emitted in all directions, it's concentrated on a 1 square millimeter area. And we all know that these light bulbs were pretty hot to the touch, like you could burn yourself touching them. And they had a relatively large area. Like the bulb had, I don't know, maybe 10 square centimeter or maybe more than that. They were about that big. So you concentrate all the power that was coming out from this light bulb onto a very, very small area. And in fact, you get a temperature, if you can concentrate all this power, all this light, and you let that small area become to thermal equilibrium, you get a temperature that's about 5800 kelvins, which is the temperature at the surface of the sun. Now let's see, for the light from the moon, well, the moon is about 1 million times less bright than the sun. So about than the sun. So the maximum concentration we could get by collecting as much moonlight as we want to would be 633 watts per square meters. And if we get our light bulb example, this is not enough to burn paper. Like even that light bulb would be very hot to the touch, but you couldn't start a fire with the light bulb. And the radius of the light bulb is about maybe 2-3 centimeters. So if you want to get all that power over a spread that covers an area of 63, that covers an area of 1 square meter, you will get a much larger radius, and it's basically, if you, let's say you're 10 centimeters for the light bulb, you would feel a bit of heat, but that wouldn't be enough to start fire. Now I want to address a few ideas that have been proposed in comments in the Physics Stack Exchange discussions that were following some of these questions, or in the comments in a column that I found in a blog post by Ask a Mathematician. That there will be a link to that also in the description, that also have some interesting physics in them. Okay, the first thing that you see mentioned when you look at the comments in these sections, or even at some answers, is that there's a paper by a guy named Cooke, published in 1992 in the journal Applied Optics. The complete reference will be in the description of the video, that said that he achieved a power concentration from sunlight of 72 watts per square meter. That is, he could achieve, using a system, a power of 72 watts per square millimeters. Well, obviously that's larger than the 62 watts per square millimeters power at the surface of the sun, and if we could concentrate that much power on a small area, we could indeed, according to them, have enough power to reach a temperature larger than temperature at the surface of the sun. And now you would see that people that discuss this paper, well, first they probably haven't read the paper, and second, they mentioned that the paper uses something called non-imaging optics, as it's something magical that allows you to go around the laws of physics. Well, that's not what happens. What is non-imaging optics? Well, imaging optics is when you take the light rays and you want to form an image. You have a lens, or you have, for example, a mirror, and you have some object, and you want something that looks a lot like the object after you're done with your treatment of the light. In non-imaging optics, you don't really care about that. So you can mangle the whole thing, and if you have an object that's got a dot here, a dot there, they could be superposed at the same spot. All kind of things could happen. And how does their non-imaging system works? It's because they have some kind of structure in the transparent material that has, I think, kind of a weird shape, and they have light coming here, and they will be like, everything will be concentrated like this. You can look at the paper if you want, and that doesn't form an image. But what people don't realize is that if you remember, there was an n squared term in our formulas earlier, and you can indeed, if you are in a medium in which the index of refraction is larger than 1, have a higher power concentration than at the surface of the sun. Now, this doesn't allow you to reach a temperature larger than the temperature at the surface of the sun. And that would contradict the laws of thermodynamics. There will be a whole video about that. But basically the idea is that when you're in a material in which the index of refraction is not 1, more power at a given temperature is emitted than in the vacuum, and everything balances out. There will be a video about that later. So this whole thing about non-imaging optics as being some kind of magic doesn't work, and you can indeed concentrate light to have a larger irradiance than at the surface of the sun, but that doesn't allow you to reach a temperature high enough. And the other idea that people have sometimes is that they say, well, let's say I have a system here that concentrates light to a very small area that allows me to reach a very high temperature, but not as high as the temperature of the sun. They say, okay, we understand, we can do this with the system. But let's say I put 2 systems like that, or 3 or 4 or 5 or 6 or 7, but at some point, let's say I get 20 watts per square millimeter with one system. If I put 4 of them, I've got 80 watts per square millimeter. So now I have a power high enough to concentrate the light as much as I want. And it could be either the same sun, and you can have a system of mirrors, like the sun emits light like this. Like them, you can have a system of mirrors that takes light that was here and just transfers it here, however you want it. And say, well, I will add up all these sources of light and I will reach the temperature I want. Well, that doesn't work for two reasons. The first one is that in the conservation étendue, we never said that the system had to be in one piece. Like, let's say I have a lens here, and I have a lens here, and light is coming, and I concentrate the light like this. I say I have two systems that works. No, étendue doesn't care that there's a gap here. Basically, this whole thing is the system. Same here. This whole thing is the system. And that won't work. And why doesn't not work? Well, it's because if you want to concentrate light a lot, as we said, we had to spread it out. Let's say you want maximal concentration. Well, we know that if we have a maximal concentration of light coming from the sun here, and it's concentrated, the light will be emitted in all directions almost, well, at 180 degrees, over the old 180 degrees when you're at maximal concentration. And if you want to collect all the light because you want to use that to heat some object, well, basically you will have to put your object here. Now, what is the problem? The problem is that, yes, you can have another system that does the same, as I said, with system of mirrors, and here. And what you've got here is you've recreated the conditions at the surface of the sun. There's enough energy so that all around you, you get 650 watts per square millimeters. But we know that at the surface of the sun, the temperature is the temperature of the surface of the sunlight. That's by definition. So this doesn't work. And if you say, well, okay, I just use less concentrations, you will always have a problem. Like there won't be any room. Like here, there's no room to input more light this way because these two things are stuck to each other. And I haven't done the math, but qualitatively, you can understand that however many sources you want to add, at some point they will need to overlap. There won't be any physical space to get the light in. And you cannot get around this limitation just by trying to have some trick of, oh, I would just sum up the power from 100 systems. That doesn't work either. And that's it for today.